Today we will continue our discussion of Vlasov theory of plasma wave, and we shall discuss Landau damping and growth of waves. First we will derive a dispersion relation for plasma wave, then deduce the damping rate, and in case of a drifting Maxwellian distribution function or bump in tail, we will examine the possibility of wave amplification giving rise to instability. We will also discuss the growth of ion acoustic wave by a drifting electron distribution function, and we will discuss the consequence of such instabilities. The references for today's presentation are the same as before, as in the last lecture: 3 books by Stex, Kroll and Triple Peace, and by F.F. Chen. Let me recapitulate what we were doing last time. We were examining the possibility of having a plasma with equilibrium distribution function F0. This was the equilibrium distribution function, perturbed by a small perturbation F1, self-consistently with the creation of an electric field, which we wrote down as having Ez is equal to minus delta phi by delta z, and we were considering that F1 was uniform in x and y. So, it was a function of t, function of z, and function of Vx, Vy, Vz in general. Phi was a function of t and z. So, a small initial perturbation in the distribution function and self-consistent electric field creation in the system, how will this perturbation will evolve in time? Will it damp out or will it continue to grow? That was the issue I was trying to address. For this purpose, we had introduced Fourier transforms, and we introduced a quantity called Fourier transform of F1, F1k, that was in Z. So, this was I had written as 1 upon under root 2 pi and integral F1 exponential of minus I k z dz minus infinity to infinity. This was the Fourier transform of F1, and Fourier transform of phi I will call as phi k is equal to 1 upon root 2 pi integral minus infinity to infinity potential multiplied by minus I k z dz. So, what we did was that we had a linearized Vlasov equation which was of this form: delta F1 by delta t plus V delta delta z of F1 is equal to minus E delta delta z of phi upon electron mass, minus E is the electron charge, multiplied by delta F0 by delta Vz, and when I multiply this equation by on both sides by exponential minus I kz dz and carry out the integration over z from minus infinity to infinity, I got an equation for F1k, and that equation was, let me write down that equation, F1k was delta F1k delta t plus Ik Vz F1k is equal to minus E upon m Ik phi k delta f0 by delta Vz. So, this is the equation governing the Fourier transform of perturbed distribution function, and this phi k is related to f1k through the Poisson's equation, which was phi k is equal to E upon k square epsilon 0, where epsilon 0 is the free space permittivity, and triple integral f1k dvx dvy dvz. You may note one thing in here, that I can easily multiply this equation by dvx dvy and integrate over vx and vy, because there is no derivative or no other coefficient having vx and vy. So, it is very simple. So, I can easily multiply this equation by dvx and dvy and integrate after all, and I can, let me define a quantity f1 k as f1k dvx dvy double integral. So, f1k dvx dvy, then this whole double integral will reduce to simply f1k. So, I can write down this is simply E upon k square epsilon 0 f1k into dvz, and this f1k will depend only on, obviously is on time, k and vz. That is all the dependence. So, but in order to obtain an equation for f1k, I multiply this equation by dvx dvy and integrate, and the f0 when I integrate over dvx dvy, I define capital F0 as f0 dvx dvy. So, this is called one dimensional distribution function, and f0 now depends only on vz, because vx vy dependence have been integrated over. So, my equation governing f1 would be, f1k would be delta delta t of f1k plus ik vz f1k is equal to minus E upon m ik phi k delta f0 by delta vz. So, it becomes a one dimensional equation as far as f is concerned, its velocity space dependence is concerned. Now, to get rid of this time dependence, we carry out a Laplace transform. A Laplace transform has to be carefully done. So, I write down f1k, which is a function of time besides other dependence, it depends on vz also. So, I write down this quantity as f1 k, let me, and omega. Now, this is a function of vz, of course, is there, exponential of minus I omega t d omega, where f1k omega is called the Fourier transform of f1k. So, I will write down f1k omega is equal to f1k, which is a function of t and vz, exponential of I omega t dt, sorry, this is dt, this goes from 0 to infinity, and there is 1 upon 2 pi in here. What I am saying here is this Fourier transform I define as the time integral of my distribution function multiplied by exponential I omega t. And this f1k may have a dependence on time which may go as exponential of say gamma t. Now, if this has the exponential of I gamma t or gamma t of this form, then the integration over omega, obviously I expect this goes from minus infinity to plus infinity, but then omega should be allowed to have a imaginary part large enough so that the exponential decay part of this is more dominant than the exponential growth part of this. Otherwise, this will overflow, because in this integral, if omega has a large imaginary part, it does not have a large imaginary part, but this has, then as time goes on, this integral will overflow. So, this integral should not be overflowed, and hence this omega should be allowed to have a imaginary part which is substantially large, because any imaginary part in omega will be minus. So, suppose I write here this omega as omega real plus I times omega imaginary, then this term will go as exponential minus omega I into t. What I want, that this integral should not diverge. So, whenever this perturbation has a time dependence of this form, the time dependence of this exponential part should be more dominant than this one, so that this integral converges, otherwise this will not converge. So, means this is defined only for for those values of omega for imaginary part is substantially bigger than gamma. That is important. So, when I carry out this limit, I must be careful, this goes from minus infinity to infinity, but it should have a substantially large imaginary part plus I times some imaginary part, suppose alpha, plus I times alpha. Alpha is like any quantity greater than gamma. That is important. So, if I have to carry out this, if I write down this, suppose I plot real part of omega here and imaginary part of omega here, and I find that the Fourier transform has, or suppose this is the value or these are the values, any value, suppose this is the value, imaginary part omega, f1k suppose has a dependence on time which is equivalent to imaginary part of omega equal to so much like gamma, then my line of integration should be here. This is the line of integration of omega integral from minus infinity to plus infinity, but at a height alpha. This is primarily the thing. Means any singularity in the Laplace transform should be below the line of integration. This is what we have to say. So, when we carry out the inverse Laplace transform, we should be careful about it. But I think we will defer this discussion to a little later stage. Let me first go back to our Fourier transformed Vlasov equation. What I do, multiply the Vlasov equation for f1k by exponential of I omega t dt and carry out the time integral. Let us see. The first term in the equation is delta delta t of f1k, multiply this by fi x omega t dt and integrate. Let us see what do I get. I am doing this from 0 to infinity. This quantity will be, first integral of this quantity will be f1k, and f1k as I mentioned depends on time, and Vz, this has to be obtained at two limits, multiplied by exponential of I omega t. The limits are from 0 to infinity, minus differential of this and integral of this. So becomes f1k, and differential of this is I omega, exponential of I omega t dt 0 to infinity. As I mentioned to you, omega has a substantially large imaginary part. So when t goes to infinity, this vanishes. So at the upper limit, this entire quantity goes to 0. Only at the lower value this will survive, and at this quantity is 1, and this is f1k 0 Vz. How about this integral? If I take I omega outside, then this is simply the Laplace transform of f1k. So then this integral is simply sum of two terms. This integral delta delta t of f1k exponential of I omega t dt, which was from 0 to infinity, is equal to minus f1k at 0 Vz minus second integral was simply f1 k omega into I omega. And then the velocity equation becomes simple. It simply gives you f1 k omega is equal to, simply simplify this, E upon m omega minus k Vz, k here, phi k there, into delta f0 by delta Vz. So we got a simple expression for f1k. Now let me go over to the expression for phi k. I have written, so if I multiply phi k equation also by exponential I omega t dt and integrate, I will get phi k omega is equal to E upon k square epsilon 0 multiplied by dvz integral from minus infinity to infinity multiplied by f1, this is capital F1, this is capital F1, capital F1 k omega, this is all. I think I forgot to write this term, this is also a term there. So when I multiply this, take this on the right hand side, it becomes plus, actually when this goes on the right hand side, it becomes minus 1 up, this becomes f1k 0 Vz divided by omega minus k Vz into I. This term I have taken into account. I had forgotten to take this into consideration, so that I should add. Now these two equations, this is phi k omega also here. My suggestion is that, or rather what I want to do now, I would like to use this value of f1 k omega here, and I will get two terms. One on the right hand side will contain a phi k omega that I will combine with this term, and I will get another term having this integral dvz of this quantity. So let me write down phi k omega I get is equal to some numerator divided by the denominator. Numerator turns out to be an integral which is, if I simplify this, is E upon k square epsilon 0 into I k common, and then you will get an integral of this form f1 k at 0 Vz dVz upon Vz minus omega by k, minus infinity to plus infinity, and the denominator of this is, it is 1 minus, let me just see, the denominator is rather simple. Let me write down this expression. This turns out to be equal to omega p square upon k square into 1 upon n0, I would say here n0, the number of electrons per unit volume, into minus infinity to infinity delta f0 upon delta Vz upon Vz minus omega by k. So you get the Fourier Laplace transform of wave potential as a ratio of two quantities n and d, and here omega p I have defined as n0 e square, omega p square is n0 e square upon m epsilon 0, but because there was no n0 explicitly there, so I have multiplied denominator numerator by n0, and this is how I have written. But obviously one n0 is contained in the distribution function f0. The important contribution of Landau lies in understanding this. The thing is that whenever you carry out the Laplace transform, you have to integrate to obtain phi from phi k omega. I have to carry out the inverse Laplace transform or integration over d omega from minus infinity to plus infinity above all the poles, and that is a complicated integral. Landau says that if d equal to 0 has the singularities, now obviously this is integral, this can be 0 if it is 0 for some values of omega. After all, omega is a range and complex frequencies, so for some values of omega this will be 0. Those values of omega for which d is 0 are called poles of phi k omega, and the maximum contribution to any integral will arise from those poles. But unfortunately, your Laplace transform is not defined for those frequencies complex omegas at which this becomes 0. So then you have to carry out what we call as the analytic continuation of this integral. Means of this Laplace transform has to be, this is essentially a quantity defined in complex omega plane. So you want to define Laplace transform in a domain where singularities lie. So let me draw a graph here. Suppose I plot here real part of omega and imaginary part of omega here. D, the denominator of the Laplace transform, suppose becomes 0 at some point here. it may become 0 somewhere here. Then your integration has to be carried out on this line. This is the contour for omega. Integration has to be carried out here. This is contour 1. Landau says that if there are no poles between here and this line, so if I choose this, suppose this is another path of integration, this is path 2, because please always keep this in view. I want phi k at time t that I write in terms of phi k omega exponential minus I omega t d omega, range is minus infinity plus plus I alpha to infinity plus I alpha. This length is I alpha from here to here, and this is 1 upon 2 pi. So in order to carry out this integration over this line in the complex plane like this, Landau says that it will be much easier to carry out a integration of this over another path which is far below the imaginary omega equal to 0 axis. This is the line over which imaginary omega is 0. So go underneath, because imaginary omega will be highly negative. So when omega has a large negative imaginary part, this quantity will vanish. So only contribution will come from the poles. So Landau suggested that rather than carrying out integration over here, it is more convenient to carry out integration over here, because only the contribution from poles will come. But then your function is not defined below the singularity line, because as I mentioned to you, otherwise the Laplace integral overflow. So in order to avoid the overflow of the Laplace integral, you defined your Laplace transform only in upper plane above the singularity. The issue was that how will you generalize your function? Now let me define what is analytic continuation. Suppose in my complex plane some function is defined in some domain. This is function f1 is defined, and another function is defined f2 in some other domain. This f2 function is defined here. But if in this overlap region f1 is equal to f2, then we say that f2 is the analytical continuation of f1. This overlap region may be a simple surface or single line, a single curve. It need not be a big finite area region. The area of this may be negligibly small. It could be simple joining line. So continuation of f1 to f2, f2 is called analytic continuation of f1 if in the overlap region the two functions are equal, or at the boundary joining the two functions are equal, then this is called analytic continuation. And what is a function when it is analytic continuation? A function is called analytic when the derivative of the function you can define. Suppose there is a function g, a function of z, you call this analytic when g has a real part function of x and y. Suppose that z I write as x plus iy, then this function can be written as u of xy and v of xy. U and v are called the real and imaginary parts of g function, and x and y are called the real part, imaginary part of z function, of z variable. And there is a condition that when delta uy, some derivative of this with respect to x or y is related to some derivative of y or v with respect to other variable, means the differential coefficient of g is uniquely defined irrespective of, suppose there is a function is defined at this point here and it is defined its neighborhood. When you go from one point to another point, either from here to here or from here to here or from here to here or from here to here, it gives the same limit. then the function is called analytic. So when the derivative does not depend on how z goes to 0, we define normally g at z plus dz minus g at z divided by dz and limit dz going to 0. This is called g prime. But dz can go to 0 in a horizontal line or a vertical line. But when you give an increment from here to here or here to here, if the rate of increment is same, then only the function is called analytic. Means it is independent of whether you make dx equal to 0 or dy equal to 0. So on which route you move, then the function is called analytic. So the thing is that if my function is analytic in some domain, the analytic continuation can be achieved by detouring the path of, after all, the Fourier transform that we obtain here are in the form of integral over Vz. So Landau suggested that why don't we treat Vz as a complex variable. Normally the integral in these n and d, the two numerator and denominator of phi k omega, they contain integrals over Vz. He suggested that treat Vz as a complex variable. And presume that those functions, n and d functions that you have written, if they are analytical in a certain region, and if you can avoid the singularity, then in all the domains where singularities do not exist, the function will be analytically continuous. So what he suggested was this, that if I have to carry out, suppose I look at this n expression, n is equal to E upon k square epsilon 0 I k minus infinity to infinity f1k 0 Vz dVz, this is the initial perturbation, upon Vz minus omega by k. This is some function of omega by k. So what Landau suggested, that in order to carry out this integration, what you are having is this. Suppose I plot a real part of V, this integration is over real Vz, but he says that in order to look for analytical continuation of Laplace transform, I treat Vz as a complex variable. So real part of Vz if I plot here, imaginary part of Vz I plot here. What do I get? If I move on this horizontal line, my integration has to be carried on the horizontal line. But this omega by k with finite imaginary part omega, I can have a pole here or I can have a pole underneath. Suppose pole is here, then he says that this integration over this line is the same as over this line this is, suppose he calls path 3, this is path 4. The integral along this line and integral along this line, they will differ only by the contribution of the singularity, a residue of this pole. And if you have a pole underneath here, Landau suggested then your path integral should be like this, go over this line, go underneath and surround this here, and so line integral, this was a suggestion that the line integral from here to here is the same as line integral over this path plus contribution from the singularity, and you will have the contribution of singularity here as well if the contribution, this singularity lies underneath the imaginary Vz line. then you detour your contour like this, then n defined by this integral, this deformed contour will be analytically continuous, and your Laplace transform is then valid in the domain where imaginary part of omega is negative and far negative. So, just by detouring this, he could show that for imaginary part of omega higher values, certainly this is the same, because if the singularity lies here and your function is defined, there is no problem. The problem arises when the pole lies here, so he says deform the contour. So, what he wrote was this, and the same thing was done for D. D was written as 1 minus omega p square, denominator was k square n0, delta f0 by delta vz upon vz minus omega by k dvz. This is equal to 0 are the poles. When I put this equal to 0, they are the poles. So, they say that if imaginary omega is greater than 0, means the poles lie here, then the zeros of D will be given by this integral when you are carrying out the integration over the real line. Whereas, if your poles lie imaginary part omega is less than 0, then you have to detour the contour, and this is 1 minus omega p square k square n0 minus infinity to infinity delta f0 by delta vz upon vz minus omega by k dvz. A contribution from the singularity has to be added. So, he added a term here which turns out to be equal to, when you add a contribution to singularity, it is 2 pi I times the residue, and it turns out to be equal to 2 pi I times omega p square upon k square n into delta f0 by delta vz at vz is equal to omega by k. This is the additional term that he added. So, Landau says that whenever imaginary part of omega is less than 0, in that case, because I wanted to really bring my contour to carry out inverse Laplace transform to imaginary omega being very negative, in that case he says that detour this contour by this, and contour defined like this will be analytically continuous. And then he says that these two can be written together in the form of a single, make a single statement by using what we call as principal value. You define principal value of a integral through an isolated, well, let me just define this. The principal value of an integral is defined as the, well, suppose there is a pole somewhere through an isolated singular point called a pole. Is the average of line integrals above and below the pole. So, you are considering two line integrals, there is a pole somewhere just above, just below. Carry out the line integrals here and there, and average sum, average of the two will be called the principal value. And if you write this in the terms of principal value, then denominator of this Fourier Laplace transform will be 0 correspond to 1 minus omega p square upon k square, and p means principal value of this integral minus infinity plus infinity, that is along the vz axis, real vz axis, delta f0 by delta vz divided by vz minus omega by k dvz minus I pi omega p square by k square n0 is here as well, multiplied by delta f0 delta vz at vz is equal to omega by k, and put this is equal to 0, and this is the dispersion relation, because the values of omega which satisfy this equation, in general those values are complex, and your phi k at time t will go as exponential of minus I omega t, where omega are the values which satisfy this equation. Let me call them as omega prime values. So, omega prime are the roots of this equation. So, the entire problem of examining the growth or decay of perturbations boils down to obtaining the zeros of this equation. This equation is an integral equation. The first integral, or there is only one integral, has a velocity space integral from minus infinity to plus infinity, but this omega you have to allow complex values to omega, and principal value I have just defined as the average of line integrals just above the pole and just below the pole. And this is the additional contribution that gives rise to damping of waves. If this were not there, as Vlasov actually did this theory of plasma waves prior to Landau, and he did not get any damping because he did not treat this singularity carefully. So, when you put this is equal to 0, you do not get any damping of wave. But this is the additional term that you have to keep in view that gives rise to damping of the wave. Well, I think this entire mathematics can be put in a much simpler way. The entire exercise was actually I carried out just to show you that if you consider initial value problem, then you have to carry out the analytic continuation of the function. And in search of analytic continuation, Landau detoured the contour of Vz integral, treating Vz as a complex variable. But once you have recognized that whenever you are encountered with the Vz integral or integration velocity space, you will follow the Landau prescription, then the rest of the procedure is very trivial, very simple. And I would like to rework out the solution of Vlasov equation. What we were really having is, let me write down the Vlasov equation again. Delta f by delta t plus v dot del f minus e, rather plus e, delta delta z of phi delta f0 by delta vz equal to 0. This was the one dimensional, this was the Vlasov equation. I can write this z component here and this z here, forget this. So, this was my Vlasov equation which I wanted to solve, and I can solve this very easily, saying that f is equal to f0 plus f1. I linearized this and my equation became delta f1 by delta t plus vz delta f by delta z, this f1, is equal to minus e delta delta z of phi delta f0 by delta vz. This is all. So, rather than doing any Laplace or Fourier transform, I consider, suppose my phi is equal to a exponential minus I omega t minus kz. I presume a Fourier component, Fourier Laplace component of phi, and I want to find out what is the response of my f1 in quasi steady state. Then I will say that my f1 should also have a similar dependence on t and z. So I say that f1 should also have as a exponential minus I omega t minus kz. Substitute this back in here, replace delta delta t by minus I omega, delta delta z by ik, and this equation becomes simple. F1 becomes equal to E k phi upon m omega minus k vz into delta f0 by delta vz. Simple. How about the density perturbation? N1 is equal to f1 dvx dvy dvz triple integral. Substitute this in here. This becomes E k phi upon m outside. I can take minus k common also. So take minus here and k outside here. In the interior you get delta f0 upon delta vz upon vz minus omega upon k, and this is d v z dx dvx dvy triple integral. The denominator does not depend on vx vy. The derivative is also not with respect to vz, it is simply with respect to vz. So what I can do for a special case, when I take f0 to be Maxwellian, which is equal to n0 pi to the power minus 3 half v thermal to the power minus 3 exponential minus vx square plus vy square plus vz square divided by 2te. This is the distribution function f0 for a Maxwellian distribution function. My suggestion is that when you do this, then when you carry out delta delta vz, this factor, exponential factor, can be taken out of the differential operator, and you can carry out the integration over vx and vy. When you do this, then limits on all components of vx, vy, vz are from minus infinity to plus infinity. So on carrying out vx, vy integrations, this turns out to be, and recognizing that minus infinity to infinity exponential minus x square dx is equal to root pi. If you recognize this, then this integral turns out to be n1 is equal to minus e k phi upon mk. You will get n0 there upon under root pi, you get rest of things cancel out, and 1 v thermal you get, and you get here delta f0 by delta vz upon vz minus omega by k and dvz minus infinity to infinity. And if you substitute for, well, what is f0? f0 is called one-dimensional distribution function. Actually, I made a mistake. This n0 is not there. that is involved in F0. This is equal to N0. Actually, all these factors are not there, they are in a part of F0. So, let me remove them here, they are not there. N0 upon under root pi into V thermal exponential minus Vz square upon V thermal square. This is called one dimensional distribution function. Now, when I substitute this back in here, this integral takes a simple form, and let me write down this. N1 is equal to E phi upon m, k will cancel out, you will get N0 outside, so N0, negative sign is already there, pi to the power half, then you have V thermal here, and if I differentiate this function, you will get twice Vz upon V thermal square into exponential. So, here you get with a negative sign, so minus is here, 2 will be there and V thermal cube will be there, and you get here Vz exponential minus Vz square upon V thermal square divided by Vz minus omega by k dVz. This goes from minus infinity to infinity. People normally define Vz by V thermal as a new variable. Let me call this as P. So, Vz upon V thermal, let me call a new variable called P. And let me define omega by k V thermal as a quantity called xi. Then this integral takes the following form, and one turns out to be exactly equal to, this is equal to 2n0e phi upon m pi under root into V thermal square, and you get this integral of the form P exponential minus P square upon P minus xi dP minus infinity to infinity. I define a function called z function of xi identically equal to 1 upon under root pi exponential minus P square upon P minus xi dP. This is called plasma dispersion function. Limits are from minus infinity to infinity, and in carrying out this integration one should be careful. This is not only the principal value, this has to add a term corresponding to the Landau prescription. So, the entire understanding of or analysis of Landau is contained in the interpretation of this integral, not only principal value, but the additional imaginary term that I had added because of the going around the singularity. So, now this P can be replaced by P minus xi plus xi, and when P minus xi term cancels with this gives you root pi. So, it becomes a simple expression, and this xi can be taken out and you get this entire expression in a simple way, neat way. And let me write down this. It becomes n1 is equal to twice n0 e upon m V thermal square into phi here 1 plus xi, z function of xi. This is a very important deduction. The perturbed electron density due to the plasma wave is related to this expression. This is the expression for it. And I would like to substitute this in the Poisson equation. The Poisson equation is del square phi is equal to minus, rather plus n1 upon epsilon 0. Replace this by minus k square. So, you will get phi is equal to minus n1 upon k square epsilon 0, and when I substitute this here, you will get this is equal to 2 omega p square upon k square V thermal square with a negative sign into 1 plus xi z of xi. And this entire quantity can be written as minus chi e into phi. So, chi e, that is called the electron susceptibility, is twice omega p square upon k square V thermal square into 1 plus xi and plasma dispersion function of xi. And this equation gives you the dispersion relation for plasma waves, 1 plus chi e equal to 0. So, this is a very important thing, that 1 plus chi e is equal to 0 is the dispersion relation for plasma waves. We do not have time today to discuss its implications. I think we need to need one more lecture to discuss its implications. I think we shall continue next time in discussing the dispersion relation and obtaining the damping, etc., damping rate of the wave. Probably I would like to close at this point, but let me remind you that the entire contribution of Landau really lies in reinterpreting the integral over v dvz in the dispersion relation. And when you properly carry out the integration following Landau's contour, Landau's prescription, you always get an additional term that contains the derivative of the distribution function delta f0 by delta vz. As I mentioned to you, physically we were expecting that you will get growth or damping of the wave when the distribution function has a positive or negative slope at the phase velocity of the wave, when vz is equal to omega by k, and the same thing is contained explicitly in Landau's prescription. I think we shall discuss this in our next lecture. Thank you.